Welcome Raiders. B7H30 brought 27 friends to the party. Go drop them a follow.
Thanks so much for the
Theo
raid.
says,
Riffraff inbound. Tomb Raid B7H30 Tall B7H30 Rev Shell Roll B7H30 Xa.
Fan says,
Yeah, I was eating this
Dobra.
very tasty thing, you know. It's blueberry jam and then there's this vanilla rice thing.
Theo says,
Do you want some,
Stream starts
Nori?
now.
Yeah.
LG.
translated from German. Kitty says,
So I haven't really started
We
yet.
here for the snacks, we here for the snacks, we here for the snacks, Noiki one nom. Yes, yes, Noiki one you.
translated
Yeah.
from Indonesian.
So we're going to do this, continue this buffer overflow room. And the last one, with overriding function pointers, we had to look up a lot of stuff outside the room because it doesn't say anything really how to do this. Which is kind of funny. It's supposed to be a learning room, right? We didn't. We had to learn stuff outside the room to find this. Yeah. So we'll see what the next task 8 here is and what the last one is too. And hope to learn a lot more. And thank you again for the raid. What were you doing on stream? Tell me. Also, it must be kind of early, right? Already raiding?
Theo says,
No CL, UE. LOL. Hack the box. As boxing.
translated from French.
Okay. Yeah, so you're going for the OSCP now.
As boxes.
Nice. So your new job will pay, I guess, right? Because it's a bit expensive, isn't it? Might be. Or maybe just privately doing it.
I am. The new job is paying LFG.
Kitty
Great,
says,
great.
I mean, we all bully him a little. Well, some of us. Okay, just mainly Noiki one boba. Mainly me.
Okay, yeah, so let's actually get started with this. So I usually start like at 30 in my time, but I was still working at I worked as a consultant on an electronics company a bit away here for a few hours. So
Theo
I thought
says,
I'd do 3 hours.
Mainly
at
Nori.
least.
Stare.
Mainly Nori. Oh, you had to be kind to Theo, right? You had to be kind. So, let's log into this one. Logging into my
Got to get ready for work.
machine.
Have a great
Okay.
stream.
Yeah, have a great time at work. And that's why you're so early, right? Because it's before work stream. Right, I get it. Ah, yeah, so...
Fix it 42 loves.
Yeah, lots of love and good luck. So it'll be
Kitty
almost
says,
a week for you now, right?
But Theo no feed me like you do. Snacks keep me calm, Noiki one nom.
Okay, so that's why you're so kind to me. Okay. Yeah, so finally I did find this address here. And this wasn't extremely hard to find, but I am very curious why it keeps working. Even if I restarted the box, it's still the same address here. Yeah, so I was thinking, is this like a relative address inside the program? I asked ChatGPT and it said no. I don't trust it, of course, but I don't have a good source of information here. So let's see. Alright, I was just checking that old file we made. Let's see here.
Fixerbot says,
New follower Quan K. Less than 3.
Welcome in, welcome in. So, I guess I will scroll up a lot here, right? Because it kind of takes space when you output the memory contents. So we connected by SSH to this machine. It's the same one we have now. I'm not starting it and we really need it because it will just time out, right? This is the directories we have in there, and we were going for number 2 here last time. And this is the program. So it's a simple C program with 3 functions: special, normal, and other. Why is this there? And the main function here, where the program is started, if you don't know, see, this is where it starts running. It just declares an int that's a pointer to the function normal here. So we need to get we needed to get the, you know, address of this to put in here, the pointer. And then it has this char buffer that we can overflow when it asks for characters in there. And this is not a safe function, so we can just do, instead of 14, we can do a lot of characters, right? And this is what we did. Oh, that's not the first time that happened. I closed what I was going to look at, and that's not good. That's very annoying. Yeah, I should start, like, putting everything into files. Log everything to files. So I clicked with my right mouse button by mistake there and closed it. Whatever, we have it still, and I have it in my head. Anyway, so
New
this
follower
function
Brian
asks
Taboy.
for text
Less than
in.
3.
Thank you for the follow. And when we input more than 14 characters, it's actually inputted into this variable. So that's how the buffer overflow here works. And then after this, let's see. Yeah,
Brian
it runs the
Taboy gifted
function
a tier
where
1
this
sub to
is.
Rizopmarepis.
Oh, thank you so much.
Thanks so much, Brian Taboy, for gifting a
Thank
sub to
you.
Rizop Marepis. Less than 3.
Thank you. Oh. Yeah, so we need to change so that our function that we want to run here is run instead of the normal one, which is it's initialized to here. And that's what we were doing last time, and I was just testing around stuff with right,
Brian
so
Taboy
R2
says,
they had
Hey, I
already.
voice it's THA not TA, come on.
Yeah. So, just reading chat too, not just listening to it. Too bad I closed down the window. I was going to put in my notes to the stuff. Right, so a lot of stuff. We checked addresses. I think I really would have wanted that stuff that we lost. That doesn't matter. We'll just have to do it again. Yeah, so we were running GDB a lot here to look at stuff and learning how it works to get 1,000 decimals in this case at this address. This is the command, and the help, I think if I scroll up like a million years we will get the help text there. So we can do octal, hex, decimal, unsigned decimal. That's what I should have used when I did the decimal, because we got minuses. T for binary, floats, addresses, instruction, character, and string. And I think character also just prints their number. So let's scroll down, like a few thousand characters printed from memory. Yeah, so here's where I tried the decimal. We tried... is this the character one? So... I didn't want to scroll up, so I printed the help again there. Just help for this command. Or rather... yeah, I did all of that. Anyway, the command itself is the X, I guess, and then you have part of it printed together like that. It's kind of odd one, right? It's not like natural. And again, 1,000. So I should have decreased the number. We also outputted binary. I think it was there at the top. So, right, and we actually looked at other functions too, because we didn't just want to print all of the memory, because it's kind of hard to find stuff, right? So there is one that's called info functions, and then you get the actual addresses of the functions. Q is for quitting or quit, run or R for running the program. We can run it with input this way. So, and then we can put anything we want in the text file, of course. Let's see, what else did I do here? Started it again. Stopped it again. And then we hop to the other tab, and all of that is lost. Well, it's in the history still, what was done on my machine, but that's not a lot. It was mostly just SSHing to the other one. Yeah, I should really log everything. So someone mentioned also the other day that there are buffer overflow stuff on Pico CDF, so I created an account there. I thought I had one already, but I didn't find it, so now I have one, and I did 2 of them as a test. So we could continue doing that on stream too. There will definitely be a new user. I'm actually thinking, let's just run it. Starting it first. Oh, that's the wrong one. We don't want that big. Since I don't have these things, let's see if I put anything of it in my notes. I did. So we didn't lose it then. Not all of it, at least. So this one doesn't have SH. Yeah, we tested next. Also, we made some notes on GDB. We have all of the info commands here, for example, but at the top I have put a few of the other ones. So info frame, info functions are ones that we run. And there are a lot of stuff. There are so many commands here, so I've never seen this amount of help for a command, right? And also they all have separate help there too, so it can do so many things. So let's go to that. Info. Here we have info, we can get info about our breakpoints. We can do B or break to make a breakpoint. For example, B main, we get a break when it starts main, but also I noticed that if we just do start I or something, there seem to be I ones of a lot. Let's go to the top, because I put the main ones here at the start. So start here, start I, first instruction, and start does automatically at the main. stopping at the main. Run just runs it. Start debug the program. And start debug program stopping at the beginning of the main. So we don't have to make a breakpoint at main as they suggested us to do, and yeah. Anyway, let's get a new IP for it. So we'll have to hop here again, start it, hop over to this one, and wait for a few seconds or minutes or whatever, right? For an IP. To actually do this again, because, yeah, repetition, that's how we learn, right? And test the commands I remember from last time, and then we will continue with the next, like, task here. We can redo the function one first. Especially since I lost my tab there. Let's actually make a new tab. And so user 1 is correct. I think we got the IP there. No, 6, 5, 4, 3, 2, 1. Oh my god, that's a low IP. So the US is sleeping. We have low IPs. I think that's how it works, really. In the early in the day, you get lower IPs. So can't be established. Ooh, okay. Oh, I shouldn't read too much. So I remember it was user 1 password. Why I remember that? That's why? It's not useful to know, right? So let's look at this. We have this directory again. Let's go to the overflow 2 one first, because we want to make sure that we really know this, right? Let's cat the C file again. And here we have the special, the normal, the other. Why is this here? Yeah, I don't know why. We'll have to think of another reason to test something else, probably, right? It's not like we're asking, we're not getting flags here, we're just saying, yeah, we did this, you know? I think the next one actually is, so we're supposed to get some data. But I didn't really read it. I just saw that it had... Yeah, you need to enter something here, in there. That's what I saw. So, let's do GDB again. I was also thinking to test with... yeah, this R2, you know, that the room mentions actually, and we're not using it yet, so we'll have to test more things with it. I've only used it so far in another room to get strings. It was a nice way to get strings. Right, so let's actually do... If I hop to the notes again, we have info functions. So if we do info functions, let's see, and I'm typing in the notes, info functions, right? So we have here the functions, and there are special, normal, other, and main here. Right, so when you have it started, I think it lists a lot more functions. But if we compare this to what we had last time, because I still have that at least in my notes, right? At the very end here, we have 64, 5, yeah. Special, yeah, 67, 05, 40. It's the same one. So I need to know more about how this works. If anyone has any tips for learning more how this really works and how this memory, you know, these addresses, how come they're the same all the time? And if it's not that it's like just a relative memory address, but it's an actual one, why? So when we have the address, we could just, you know, input it backwards, add 14 characters at the start, and do the thing. This is really all the information we needed here. So if we were to just queue this now, and I'm again focused on another window. So the command is let's actually echo then into it. So we're going to echo stuff into, let's do these. And this is, I guess, an old programmer's habit of making both first, and that messes up sometimes when you don't have a good shell, you know. But anyway, let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, because we know that this is the length here of this one. And after the string we put here, it will also add a null to terminate the string, but we're adding stuff at once, so I don't know how much more of the memory we will overwrite with this, really, right? So I guess we should like think more. Anyway, so if I just do so x 67, it is right, and then x and 05, and then we do x. I'll put the mouse pointer here so I can remember where we are there, and then the rest is just 0. So x, right, should 1 0 work, or do we have to do 2? I think 1 should work. This is the test. Let's test if 1 works. I'm kind of feeling it should, right? So last time we made sure that we had let's see here, so did so we've covered these, and we have 1, 2, 3 more if we want to do all of them. So this depends on how the backslash x is actually read here. So was there one more? Let's count. 1, 2, 3, 4, 5, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, let's actually do the double ones. Do I think this? Yeah, I want to test this. Let's test this one, right? So when do it as a test. So we're going to send this to func pointer, and we'll see if this works. And I'm also curious, that's also interesting, right? That it didn't do anything as output. So what did I do that didn't work now? Oh no, I did it again. It's because I was looking at my notes here, and I should have switched it. Of course, this is supposed to be a pipe. I read it the input one, I read this line and then I realized, right, I did this last time, so do you know what we have to do now? I overwrote the executable file. You're not supposed to overwrite the executable file you're playing with, right? That's not a smart thing to do, so I'm restarting it. Oh, well. I guess you should see this is learning, right? Though apparently I definitely knew this before, and then I still was just going from my notes, and I was like, I was changing it, but not good enough. So, such a stupid mistake. Oh well, I have time to take a few bites of my lunch. And I will get those messages removed.
Best viewers on web link.
So I was listening to Security Now. Let's see. Twitch. We have a new IP. I'm learning the new app. I got in kind of quick on clicking my way through to the chat and stuff. So there. I better delete those messages. The new IP is 15. 15.3. We're getting short IPs. So, still user 1 password. And we're still here. So I will just let me not run this one now, right? That will be even more crazy. So I don't know why. You know,
Madam Fabulous says,
we need to CD.
Late riffraff.
Hi. Welcome in. Welcome back. So, I was stupid, and I was writing from my notes, reading a tiny bit from my notes, and I had an arrow into a file first. So, I overwrote the file. I had to restart it. So let's see. Isn't it here? Yeah, func pointer. Right. We need to // it. So now we get this is special function. You did this, my friend, and let's do the other one too. So we have this instead. The only thing we need to change is the 93, right? So if we go here again and we change 67 to 93, we get, why is this here? We don't know, but now we tested them all, you know? And let's actually make notes now. So, we want the, let's see here, the start here of this, and we're catting the code for the function. We're starting and we're starting GDP, we're running info functions. We're getting the address for the function. We're quitting this, and then
Arduku says,
didn't think very good.
did you try to work on a copy? So you don't need to restart?
Yeah, but you should never override it anyway. It was just me reading. You know, I was reading this line here. I was looking at this a bit while I was typing, and since I put it in a file first, you know, and did this. So that was bad. That was just stupid. And I don't mind restarting it if I do something that stupid. It's like learning, right? So let's put the rest of it here too. So we were just repeating what we did yesterday in a quicker way. And I looked a lot. I was very tired yesterday too because I hadn't slept that well, and yeah. Let's just put this. Also, the IP is different. So it looks a bit funny in the notes, but whatever, you know. So yeah, so I went into the directory. LSLade. Let's copy this bit too. Also, by mistake I deleted my tab. So, well, this looks a bit funny with different IPs, but that's the way it is. So, this file should probably have a better name, like tsham buffer overflow 2, and I'm thinking we'll make a new one that's actually 3, which we'll do now, right? So now let's do the new stuff and see what the new challenge is, and hope that they actually tell us stuff. But I noticed that this one actually has more text, so so they jumped here from giving us, oh yeah, you should buffer overflow this into this variable, and if you manage to change the value of it, then you succeeded, you know. And then they said do the function. So there was no information here on how. So I had to find it myself. Let's read now. Buffer overflows. For this example, look at overflow 3 folder. Inside this folder, you'll find the following C code. So let's just hop there. So, 3. So sometimes I put the space in the wrong place. Too quick for myself. There we have the buffer overflow C secret txt that we can't read. Okay, why? So we are okay. So user 2. Okay. So that's interesting. Let's look at the code. So do you see this tiny little s here? So I'm assuming we're supposed to run a function in this or something. So let's cat b dot. So let's do main first. So here's a program that eggs out your input. Copy argv1. So our input is what's the input here. So copy arg the string char buffer 140 str copy, and this is also bad, right? This str copy. So it copies the string into the buffer. Printf buffer. Okay. So we're going to have to do more advanced stuff here. And hopefully we will learn it from the room. Let's see. So why I opened that up is because this is an image, so I can't do anything but click it. This example will cover some of the more interesting and useful things you can do with a buffer overflow. In the previous examples, we've seen that when a program takes users controlled input, it may not check the length, and thus a malicious user could overwrite values and actually change variables. In this example, in the copyArg function, we can see that the strcopy function is copying input from a string, which is argv1, which is a command line argument, to a buffer in the length 140 bytes. With the nature of strcopy, it does not check the length of the data being input, so here it's also possible to overflow the buffer. We can do something more malicious here. Let's take a look at the stack. What the stack will look like for for copyArg function. The stack exclude the stack frame for strcopy function. Stack bottom return address. Yeah, I'm thinking we're going to have to change that. Saved registers char buffer. Earlier we saw that when a function, in this case main, calls another function, in this case copyArgs, it needs to add the return address on the stack so the callee function copyArgs knows where to transfer controls once it's finished executing. From the stack above, we know that data will be copied upwards from the buffer 0 to buffer 140. Since we can overflow the buffer, it also follows that we can overflow the return address with our own value. We can control where the function returns and change the flow of execution of the program. Very cool, right? Yeah, but how? Now that we know we can control the flow of execution by directing the return address to some memory address. How do we actually do something useful with this? This is where shellcode comes in. Shellcode quite literally is code that will open up a shell. More specifically, it is binary instructions that can be executed. Since shellcode is just machine code in the form of binary instructions, you can usually start off by writing a C program to do what you want. Compile it into assembly and extract the hex characters. Alternatively, it would involve writing your own assembly. Yeah. So why? Yeah, because C is easier. For now, we'll use this shell code that opens up a basic shell. So let's not memorize this, right? So why don't we looking at actually executing this shellcode? The basic idea that we need to point the overwritten return address to the shellcode, but where do we actually store the shellcode, and what actual address do we point it at? Yeah. Why don't we store the shellcode in the buffer? Because we know the address at the beginning of the buffer. We can just overwrite the return address to point at the start of the buffer. Yeah. So, find out the address of the start of the buffer and the start address of the return address. This is funny, but it's correct. Knackar du gubben? So my kid wants me. Just a sec. Egentligen sa jag väl att det är vardagar. See, he just wanted to ask if he could take something. Like ice cream. Calculate the difference between these addresses so you know how much data to enter to overflow. Start out by entering the shellcode in a buffer, entering random data between the shellcode and the return address, and the address of the buffer in the return address. Yeah. So, we don't know at all what this is, the amount of data it is. In theory, this looks like it would work quite well. However, memory addresses may not be the same on different systems, even across the same computer when the program is recompiled. So, we can make this more flexible. Oh, also this, when the program is recompiled. So why does it only change when it's recompiled? The difference then, I guess. So we can make this more flexible using a NUP instruction. Okay. NUP instruction is no upgrading instruction. When the system processes this instruction, it does nothing. It carries on execution. A NUP instruction is represented using 90. Putting NUP as a part of the payload means an attacker can jump anywhere in the memory region that includes NUP and eventually reach intended instructions. So if there's a lot of do nothing, we can hop at the start or at the end. We will still get to our stuff at the end, right? Eventually reach the intended instructions. This is what an injection vector would look like. So we put this at the very end there. Use Python, okay. Yeah, so we can just print this times 30. So I still want more information, you know, about everything. In some cases, you may need to pass exarchs before program name. Yeah. So So from this, I'm also assuming we have Python there. But this is not enough for me to understand exactly what to do. I don't want to test stuff, I want to know stuff, you know?
Know that we know we can control the flow of execution by directing the return address to some memory address. How do we actually do something useful with this? This is where shellcode comes in. Shellcode quite literally is code that will open up a shell. More specifically, it is binary instructions that can be executed. Since shellcode is just machine code, in the form of binary instructions, you can usually start it by writing a C program to do what you want, compile it into assembly and extract the hex characters. Alternatively, it would involve writing your own assembly. For now, we'll use the shellcode that opens up a basic shell.
So, we got this from so let's just keep that. So this is what we have. Oh my goodness. Hopping to the other screen instead of to the other program. So why don't we looking at actually so these so why don't we looking I'm sorry, it's you're just thrown off a tiny bit there. The basic idea is to point our written return address to the shellcode. We want to store the shellcode. So this is of course why we have this giant buffer this time of 140 characters. So we only store the shellcode in the buffer. Because we know the address is the beginning of the buffer. We can just overwrite the return address to point to the start of the buffer. Yeah, so what I didn't do, what I was thinking about for the last task here, is to do it also with, get this information with R2, right? And that's what it actually suggests to use. Alright, and this was the me asking ChatGPT stuff last stream too, yesterday. Programs. So this is so much more complicated. Well, I guess it might not be, but we have all the text here, right? So what do we search for? What we looked for last time was get function, right? So if we do the command from the other one, it was info functions. So we want information on functions here too. Info registers, display function address, reference commands. Oh. Yeah. So this is how we can see them, you know? Here's GDB that we used. What will it be in R2? And it also has other ones. Ada Pro, WinDBG, debug. So these are not available. Hex mode, import, exports, edit, graph view. So if we focus on this and this here, dr all to get registers. So what we also want, you know, so we're almost at the end here of the list. So if we search for functions here, so why doesn't it have this in this column? Because that's alright, because it's not info, it's list. And I was thinking of searching list functions because that's like normal. So AFLIS. Right, so I remember that A is the command line thing and AAA is the command when you already have it started, right? And it gets all information. I guess this is even more than all the information. It sounds like that with an extra A on both. So what happens if we do this? We're in the new directory already, but I'm now very curious, right? We can do it on this executor, but it also has functions. So if we were to do here GDE and of course executable name, and then we do info functions, we get this. And if we do info registers, so here we have the copy arg function if we were to need that ever, you know. We don't, but info registers. What did I do? Oh. The program has no registers now, so we might need to start it first. But what I'm curious about is Right, so let's actually do the start one, right? The word is, it's the same as run, but it stops at main automatically. So it's a breakpoint in main automatically when we just start. And now it should be started, and there should be registers there. So if we were to be curious about things there, that's the start of main. Main +4. So also in this room we had a lot of information that's so long ago now, so I was almost forgetting it was in here. Let's see. Here was just like heap and stack, and then we had about frames, function frames. Yeah, I think it's the next one. So the command push it to address the next instruction onto the stack. In this case, address of the instruction on the line that contains mul ex, a local for h, stack pointer RSP, and change the frame pointer RBP to point to start of new frame. Yeah, so this is what I was thinking of here. So here we can see that they are the same, right? On this one, both of these. They really need to do this a lot more for this to be like really comfy, right? I'm like, should I do something else before to learn more? Because I don't want to like, oh, I have to go to the next room in the path on TryHackMe, you know? That kind of thing. So yeah, I shouldn't write this on paper, I should write this in notes. So did we make any notes on this before? I kind of think we might have. Did we add anything here more on links? No. Yeah, that's, I was just showing notes. Yeah, so we need to put this somewhere. We might do it here. So what do I have here? Oh, this is, I don't know really where this comes from. Anyone who knows? I don't remember. So this was from my old notes that I put into Obsidian. So I think it was up because we were looking through, as we were sorting this into this structure here. Right. Then we had these two TryHackMe rooms that I did a long time ago. And these are actually the full rooms copied. I used to do that for some reason, but it takes too much time, really. This is just the full rooms with the answers and stuff, you know. So what was I looking for? If there was anything useful in here? Just quick scanning it. Moving up, shift right. And there flags. Very good, Linus. So he ate ice cream and started coughing. Was it too cold, maybe? Yeah. So this isn't that long ago. I mean, it's like a year, maybe. So it's not like the rest of my old knowledge that's just in my head. So now we have this up twice. That's not very useful. Let's I'm sorry, I'll just quickly look if we can close these. So are they in the same place? No, not in Explorer. So that's in Windows. And this one, I have to go there to be able to see all the alternatives. That's annoying. So this is... Alright, yeah. So I've already done this. Okay. So let's close these because I have so many tabs open here, so it's a bit messy. And this was the PicoCTF test. I just did 2 simple ones. And this was just to like check all the files. And for some reason it told us to do LSR. I still don't know why it wanted that. It was definitely useless. And then I just did I did a find and run a command on all of the files. And then it was actually the first one that was the one they wanted. Then we just had to run it from the special directory, otherwise I would have found it earlier. That's an odd way to do it. But it said when you run it to do this. So when you run decrypt in the directory, it doesn't work. You have to do it so it's files. Very odd. Very odd. But it did say that you're supposed to do that, so. Then I could have run this from find instead. I tested that and it didn't work because it gave me this error. Well. I'm thinking we'll do these. But we can close this one too. But it was for this purpose that someone sent me there, you know, for the buffer overflow stuff. So we could just test stuff. I don't want to test stuff without knowing what we're supposed to do. So let's go back. I remember I was supposed to like copy and paste this bit. Whatever, it says too little or too much. Do this, the computer pressure. So general no. So I was starting to. I made a new line here to put it on. We'll have to make better notes. We'll have to. So I'm out of water. I'll just go and get some new water. I'll bring my plate down. So I'll put it on food, but I'm actually leaving the food, not getting new food. I'll be right back.
Kitty says.
Make mine a vodka please Noiki one boba.
Madam Fabulous says.
At Noriko Neko either we proved out that water equals vodka mop nodders. Clear equals clear.
Kitty says.
Yes.
Yeah, so what do you think I'm drinking here? It's just water. Water is food too, right? So, let's see. How long were you watching that screen, really?
I tried water once. Too wet for me.
Yeah, I like water. I like almost only drink water, really. Had some tea yesterday when my throat got painful. Yeah, right. I haven't felt that today. We'll see. So, just to repeat what we've had actually for fact in this room. We had this, like what registers are usually caller saved and callee saved and stuff here, right? So far as this is a more rough example. And then we had NDNS, which is kind of obvious, right? Then we had the first one where we just were overriding the variable more than 13 characters, and we got... Well, actually, I changed this to 1 just to make sure that if we put 14 characters, it will do a null there. Null terminate the string. So then it doesn't matter if this is already null. It won't change anything. But if we put a 1 here, we can see that it actually does it there too.
Madam Fabulous says,
At Noriko Neko, the average human is 60% water. The average vodka is 60% water. Therefore, we can infer that it is only reasonable to conclude that humans and vodka are interchangeable.
Of course, right? There's no difference between vodka and people. Oh. Anyway, then we had the function one, which it didn't have a lot of information, and then we had this one that we're currently on. And we have gotten this. Let's actually make something
Kitty says,
like Googling this.
The other
right?
40% snacks. Noiki 1 nom.
Madam Fabulous says,
My logic is airtight.
The rest is snacks. Yeah. So exploit DB has this one in here. So I didn't know this kind of thing was in here. Okie dokie. So we could always look there later. Buffer overflows. TryHackMe right up, of course. Buffer overflow. What's this then? This is someone's like notes or something. I'm sorry for all the cars. Can you hear the cars driving by? It's that time of the day, I guess. Concentration when striking a bar flow. Just curious here. So then it hops to my normal one. So I was just thinking if it's mentioned the C code there. Here. Oh, docs for GDB. We can open these too.
Fan says,
Madame Fabulous Sound Logic.
Hello.
Hello.
Everybody's voices are different. That's nice, I guess. Hope I can understand all of them though. The one that GoPro uses is kind of like hard to understand sometimes. Let's see. Disassemble. Main. Yeah, there's so much to learn. So much to learn. Step into the return. Run the code with the exploit. Yeah, so I don't. Oh, here we have more stuff. Okay. So it was just lots of files that are just listed after each other? Huh? So, kinda, there's a stack C though. Okay, so it's buffer 64 gets buffer. So the files are here, it's just kinda more run. You know, it's a bit more messy than normal GitHub. If you have just one file, I've never seen before there were a guest one that had several files in it. I haven't seen that. It's more files than one. So, let's not dig too deep into this. I was just thinking to send it to ChatGPT. So let's make a new one and put it over here. And just paste this and see what it says. Yeah. I was kind of thinking so. Look, nice, eh? We can see what it does, what it actually does, and not just random numbers. And it also tells us what it is. That the assembler, because this is much more readable than this, right?
Aiden says,
Good evening. How's the buffer overflow learning
back.
coming along?
Yeah, very slowly, because I think I'm starting at the wrong end. I should have started with like relearning assembler and doing maybe the is it Pawn College is called, right? I should probably have started with those, because I feel like the TryHackMe rooms, they're always like, you know, they're not that deep, and I want the deep thing. Yeah. So in this kind of space, where did it go? Is it this one? Yeah. So in this kind of space, you can't fit that much information, right? Well, you could. You could.
Madam Fabulous says,
Have you looked at
Okay.
Czar SEC's course? That's the one that TRSH Puppy did on stream.
I don't know what she did either. I haven't looked a lot on her streams. I hop in there sometimes, but so if you wanna like tell me, I could Google, of course. So what am I looking?
Aiden says,
That's true. A low-level foundation definitely helps a lot.
Yeah, so
Madam Fabulous says,
Yeah, I'm fishing a link.
okay. So why don't we? I'm getting stuck on looking again. Why do we look at actually executing this shellcode? The basic idea is that we need... yes, I know what we need to do, but I need to know more than this information. I feel I need to know more. I want to know more. So the basic idea is that we need to point the overridden return address to the shellcode. And we're going to put the shellcode in the buffer. But there's stuff in between. Overridden saved registers here. And I don't want to I could test, just adding stuff and see what happens, but I don't want to do that. I want to know exactly all the things. Okay.
Web link.
So, thanks. Let's see what it is. Binary exploitation. So is this a free thing or is it... okay, so you can decide? Is it like this? You could just, you click enroll now and you can see this? Is that how it works? So, if you have a basic conceptual understanding of binary exploitation, specifically stack-based buffer overflows, but are quite sure that concept this course is for you. Yeah, but maybe I want even before this then. Because here you're supposed to already know buffer overflows, right? So the goal of this guide is to give an overview of modern binary exploitation mitigations, why they were introduced. Yeah, I think this is like step 2. About mitigations too, why they were introduced and how they can be defeated on a practical way. Not that
I think it's pretty intro friendly.
Okay, yeah, sure. I've never seen one of them. I've heard about Tigard, but I've never looked at anything from there. So, what did you see? Sarsec. So Sarsec and Tigard is the same thing then?
Taggart is pretty top-notch and free.
And it's free. Yeah, okay. Yeah, so I've heard people mention it, but I thought maybe it was just a YouTube. I don't know. Because people have sent YouTube links or something. Okay, so this is a company. Okay. Okie dokie. Yeah, let's click it. Why not, So, yeah, so it starts with why
Zarsec works at Taggart.
mitigations. Yeah, so I want the before stuff too.
Aiden says,
Looks like a good course. A lot don't cover the modern defenses.
Yeah, but I want more before stuff before this. But this is good too. So we actually did look at address space. The randomization is off on this machine, and that might be why we get the same address of the function every time, and it just works. Even if we just restarted the box and started several things and everything, and it's just the same always. I don't get why. Why would the function? Maybe with more people in chat, you can help me. And unfortunately I deleted stuff before, but if we just scroll up here, no. So every time I run this here, this is always the same. Why is this always the same? Why it's always 400567? I mean, shouldn't this be like the space in memory where it happened to, end up?
literally everyone says,
I would really recommend Live Overflows binary exploitation playlist for a good intro. Web link.
Okay, great. Because I need to know this. I want to know this. Why is it always the same? You know? I need to know. If you have an answer, please answer that. So, okay. Simple programming C. So, but it's kind of stepping up quickly, right? Yeah, we can do this, but I don't watch like videos on stream, and I haven't had my computer started since I stopped streaming yesterday, and I started streaming today. So, yeah, I think I've actually looked at parts of this. I have. I think I've seen some of these. Right. So I think but I might be subscribing with my main YouTube, not with this. This is a live one. So my other account. So fix it instead of fix it for it to live. Yeah, so I'm subscribed to this one. Oh. I just updated it. See if it says anything that I've seen. Oh, whatever. Yeah, it's still fixed for to live. It's a bit messy, you know? If you update a page, it usually hops to the last one you set it to. But it didn't now, so this one is still fix it. Well. I should change this one to be fixed for 2, maybe, right? Because it's fixed for 2 here. So yeah, so this is why I'm thinking I don't want to like run past just to continue this. I want to do it carefully. I don't just want to finish the path. I want to know all the things and understand everything in detail. So this is just a short bit here on this. But it's very good knowledge to have, right? It's an important bit. And yeah, not just know enough just to manage to answer the questions there, but to actually be good at it and really understand it and be able to use it for a lot of other things. That's the goal. Not to finish the path or anything.
Madam Fabulous says.
Literally everyone Ty, filing that away.
Yeah, I'm thinking we could watch videos on stream, but it feels kind of bad, right? Let's see, 3, 12, 12, 9. So they're not really long either. They're kind of short, all of them. So we could of course like look at some ones, some of them. So here's a buffer overflow with shellcode. That's what we're going to do now. Now this is 12 minutes.
Literally everyone says.
Not all are going to be relevant, and they really ramp up after a while, just FYI.
Yeah, because I noticed it was like make a simple program in C. So these first ones are very basic. So let's click this one and see what happens.
Let's move on to exploit exercise stack level 5. You should have watched the previous videos to understand how we got here. The challenge description says, stack 5 is a standard buffer overflow, this time introducing shellcode.
Yeah, so we need to know. So my kid is knocking again. I could of course leave the video on, but... Yes, Gavan? No, Ska du ha ett glas med glass till pannkakor? På riktigt? Okej, jag trodde du skojade. Vill du ha såna, det är vanliga glass? Men jag vill ha grädde också så. Okay. So, if anyone has an actual, right, by the way, this is some kind of website here too, right? So I don't think we'll watch this now, but I will go back here, and I'm thinking, does anyone have a text on this, right? Because I'm going to have to go and make food for him, and I'm thinking we could put in the text as TTS. Meanwhile, we could ask ChatGPT. So I didn't read this yet, but so please explain in detail how to use this. And we could actually use the C code we have here, right? To make it understand what we want explained. So I will do this. To use this to let's put the I'm just copying also the LSLA so it sees the permissions there. How to use this shellcode to get a shell using this, and within detail is not enough. In well, a lot of detail. It was like high detail. It might misunderstand how to use this. It might think I meant like high level. I want low level. How to use this shellcode to get a shell using this. After this, well, I guess that will be enough for me to heat up some pancakes, right? So I would prefer to have an actual page. So here's a medium. Let's look at these. First of all, it's not 3 lines. Okay. Images. A lot of images, we won't hear them. Or rather, I won't hear them downstairs and I can scroll for you guys.
Party E says, would I sound off topic if I ask whether I can use a virtual machine on a cloud provider?
I don't use cloud a lot, unfortunately. So I'll have to learn more about that too. So here we have more text, I think. But it's not long. Let's see what ChatGPT did. Yes, I don't have a... Of course you can do virtual machines. And they are like virtual machines too. So what do you mean, really? That's the question. So it all depends on the power of the machine, right? So this is... let's just start this one and I'll go make pancakes. And unfortunately, it seems to stop working that I can enable the audio for this one for you to hear me. Let's do
Overview.
this.
To exploit the buffer overflow in the provided buffer_overflow.c program and gain a shell using the given shellcode, you will analyze the vulnerable program to understand the buffer size and the overflow point. Craft a payload that includes the shellcode and the necessary padding to overwrite the return address. Run the program with the crafted payload to exploit the vulnerability and spawn a shell. Step-by-step guide. Step 1. Understand the vulnerable program. The provided C program has a function copy_arg that copies the user input into a buffer without bounds checking. This allows for a buffer overflow. C. Hashtag includes dio.h. Hashtag includes lib.h. Void copy_arg, char asterisk string. Char buffer 140. strcpy, buffer, string. Printf, %s\n, buffer. Return 0. Int main, int argc, char argv. Printf, here's a program that echoes out your input \n. Copy_arg, argv1. Key points. The buffer has a size of 140 bytes. The function strcpy does not check the length of the input, allowing an overflow. Step 2, determine buffer size and overflow point. To determine where to overwrite the return address, we need to know the size of the buffer plus the space occupied by saved registers and the return address. The buffer is 140 bytes, and assuming typical 64-bit architecture stack layout. Buffer, 140 bytes. Saved base pointer, RBP 8 bytes. Return address, 8 bytes. Total, 140 plus 8 equals 156 bytes. Step 3, craft the exploit payload. Shellcode, use the given shellcode to spawn a shell. Complete it with the necessary syscall setup. ASM. \x48 \xb9 \x2f \x62 \x69 \x6e \x2f \x73 \x68 \x00 movabs r9 0x68732 f6e69622f \x48 \xc1 \xe1 \x08 /shlr9 0x8 \x48 \xc1 \xe9 \x08 /shore r9 0x8 \x51 /push r9
TTS for
\x48
shellcode is awesome.
\x8d \x3c \x24 liberty rsp \x48 \x31 \xd2 /x or rdx rdx \x48 \x31 \xc0 /x or rax rax \xb0 \x3b /movl 59 exec syscall number \x0f \x05 syscall padding 156 to 23 shellcode size equals 133 bytes of padding. Return address pointing to the start of the shellcode. We will use a placeholder and determine the exact address during testing. Step 4, assemble the payload. The payload will consist of NOP sled, optional, to increase success chances. Shellcode. Padding. Return address. Step 5, execute the exploit. Find the return address, use a debugger like GDB to find the stack address where the shellcode will be loaded. Create payload. Python. Import struct. Shellcode equals \x48 \xb9 \x2f \x62 \x69 \x6e \x2f \x73 \x68 \x00 \x48 \xc1 \xe1 \x08 \x48 \xc1 \xe9 \x08 \x51 \x48 \x8d \x3c \x24 \x48 \x31 \xd2 \x48 \x31 \xc0 \xb0 \x3b \x0f \x05 NOP_sled equals \x90 *100 hashtag NOP sled to increase reliability. Padding equals a * 156 len NOP_sled len shellcode. Hashtag assume the shellcode starts at address 0x7FFFE510, example, replace with actual. RET_address equals struct.pack, q, 0x7FFFE510. Payload equals NOP_sled plus shellcode plus padding plus RET_address. Print, payload. Run the exploit. Bash. /buffer overflow $python3 exploit.py. This should overwrite the return address to point to the shellcode, execute it, and spawn a shell. Notes. Debugging, use GDB to step through the program and find the exact return address. Environment, ensure the environment does not have protections like ASLR or NX enabled, or bypass them. Permissions, ensure the binary has the correct permissions, set should, to escalate privileges if required.
Well, that was not in detail, or definitely not low detail, or a lot of detail that I wrote. So very annoying. How many words were this? Nothing. So I have to go and get one more thing. So let's just put this one
Buffer
on.
overflows, shellcode, and memory corruption. Jake Mellichamp. Published in Codex. 8 minutes read. August 8, 2022. Contributors, Jake Mellichamp, Stephen Griffin, Wes Bailey. Introduction. Buffer overflows and memory corruption exploits are one of the earliest of computer security issues, and the subject has accounted for countless hours of effort from both the attack and defense perspectives. The first description of a buffer overflow attack is recorded in the 142-page, 1972 U.S. Air Force publication Computer Security Technology Planning Study 1 in Section 3.2, titled The Malicious User Threat. The document asserts the fact that operating systems were not designed to be secure provides a malicious user with any number of opportunities to subvert the operating system itself. The report goes on to discuss a vulnerable program that handled pointers, noting that by supplying addresses outside the space allocated to the user's programs, it is often possible to get the monitor to obtain unauthorized data for that user, or at the very least, cause a system crash. A more succinct and canonical description of a buffer overflow attack would be difficult to find. Clearly, the focus in the early days was on making systems work, not making systems secure. That would change. While most of the early exploits can only be reproduced on a modern OS by explicitly disarming the default countermeasures, it's still instructive to learn something about the history of these attacks. Nothing within the realm of cybersecurity has been created in a vacuum, and it's often the case that methods of modern systems that seem arbitrary are rooted directly to something in the past. Understanding the history can shed greater light and understanding on the whats and whys of current platforms and their vulnerabilities. 2. Historical perspective. In the fall of 1988, a graduate student at Cornell University named Robert Tappan Morris wrote a bit of malicious code that became notorious as the Morris worm. 2. It exploited several weaknesses in Unix architecture, including a buffer overflow in the fingered network service. The worm spread rapidly through machines connected to the nascent internet and caused serious disruptions. Robert Tappan Morris. Morris insisted that he was merely demonstrating the inadequacies of current security measures on computer networks by exploiting the security defects he had discovered. His justification fell on deaf ears, and Morris became the first person to be indicted under the Computer Fraud and Abuse Act. He was later convicted and sentenced to 3 years probation and a $10,500 fine. He was able to rebound rather well though, later completing his PhD at Harvard and co-founding several tech companies including the highly successful incubator Y Combinator. His current estimated net worth is $4.9 billion. History of the buffer overflow visualized. A lot of work has been done to address this type of vulnerability over the last 3 decades. In 1997, StackGuard was announced, implementing the concept of a stack canary. The same year, a hacker going by the name Solar Designer demonstrated the return to libc attack, effectively bypassing non-executable stack countermeasures. With this discovery, heap overflows, pointer overwrites, format string attacks, and a host of other fiendishly creative exploits were developed 3 simultaneously. Defensive measures were continually bolstered in such forms as ASLR, StackGhost, PAX, and more. No matter what one side does, the other seems just ahead or on their heels. The cat and mouse game never ends. 3 stack buffer overflow concepts. With that being said, in our experiments, we will become the cat, attackers, that catches the mouse, modern stack protections. Here outlines the context of what a stack buffer overflow is. Stack buffer overflows, SBOF, have been a fundamental exploit in ELF binaries for much of history. A successful attacker can overwrite local variable data or execute malicious code. This is obviously not ideal, and is usually caused by a programmer's unawareness of how stack frames work. The process of compiling source code into an executable binary is a complex process. The source code must be pre-processed, assembled, and linked to library functions, with a linker, before finally loaded into memory, with a loader. When this process is complete, a text, data, heap, and stack segmentation are loaded into memory and used for program execution. Figure 3.1 Program Layout. The program layout will be handy in understanding the nature of SBOF attacks, but the real vulnerability lies inside the stack frame. A stack frame is a segment of memory that is created every time a function call is made. It contains the base frame pointer, EBP/RBP, a constant address marking the base of the stack pointer, ESP/RSP, which may change during the execution of a function as values are pushed or popped off the stack, a return address, EIP, and incoming function parameters. The stack buffer overflow vulnerability can be described below. Figure 1.2 The vulnerability. In order to exploit the situation, the attacker must overflow the buffer's memory with a combination of NOP commands and shellcode. The overflow should continue until the base frame pointer, EBP, is successfully overwritten. The final step of the exploit is to overwrite the return address of the stack back into the buffer, before the start of the shellcode. If these conditions can be met, then the binary in question is a liability. For exploit demonstration on Linux 32-bit x86 system. Figure 4.1 Vulnerable program. In our SBOF exploit, our buffer for input is 500 bytes in size. To start off, we have to discover 1. The distance from the start of the buffer to the return address so we can place a malicious return address in the EIP register. To do this, our team used GDB. We started by randomly selecting a small overflow of the buffer, in this case, 8 bytes over the buffer, figure 4.2. A seg fault occurs. By using the command, gdb, info registers, a user can see what registers have been affected. As we can see from the image below, we successfully overwrote the EBP register but not the EIP. The EIP is the return address. From figure 4.1, we also know the EIP is always 4 bytes past the EBP register. So we simply need to add 4 to the original number of 508, making it 512. 4.2 Stack overflow. Successfully overwriting the return address. Launching the program with the 512 characters results in the following. 4.3 Successful overwrite of the return address. Crafting a malicious payload. Using GDB we discovered that the distance between the end of the buffer and the EIP register is exactly 12 bytes. Knowing this information, we can craft a malicious payload. So, where to begin? 1. Shellcode, using HTTP URL. Our team was able to find a snippet of shellcode to execute the system call exec/bin/sh, using 43 bytes. This shellcode will launch a terminal with the current process's permissions. To return address, we need to overwrite the EIP register to point to our shellcode. Using the command, gdb, x/200wx$ESP550 we are able to read the virtual memory addresses 200 bytes near the stack base. We'll upload the shellcode somewhere in the overflowed stack, it doesn't have to be an exact value, just somewhere within the stack, and use the return address to point to the start of the shellcode. Figure 4.4 Possible return address locations. 1. NOP slide, the payload needs to be 512 bytes long, figure 4.3. We have shellcode, 43 bytes, and a return address, 40 bytes. The reason the return address is 40 bytes is to create a sort of buffer space to ensure a greater chance of success that it lands on our correct return address even if some things move slightly around in memory. After doing some quick math, 512, 40, 43 equals 429, we know that we need to fill the rest of the 429 bytes of buffer data with NOP commands. Figure 4.5 malicious payload. Executing the code. Once the Python script has been created, we run the ELF binary as any typical user would, except our buffer input is a combination of NOPs, shellcode, and return addresses. After execution, you should have a shell/terminal open and ready to use. Figure 4.6 Successful PWN. V Advanced Exploits. While this is an enlightening and instructive exercise, the fact is that this attack is not possible without at least partially disarming countermeasures in the operating system and/or the compiler. The non-executable stack feature, DEP, is a hardware-based safety feature that will prevent the malicious code from executing. The stack guard feature implements a stack canary that will also halt execution if overwritten by the simple overflow attack. Address space layout randomization can be defeated with brute force in a 32-bit machine due to the comparatively small available address space. 64-bit machines are practically invulnerable to brute force versus ASLR, but technically still not immune. 6. Conclusion. Stack overflow exploits have been around for a very long time, they remain a present and viable threat vector. Despite over 3 decades of operating system and compiler engineering, these vulnerabilities have not been completely mitigated. This begs the question, can buffer overflows ever be fully engineered out of software? The Open Web Application Security Project, OWASP, a non-profit organization working to improve software security, provides educational content relevant to the topic. Its online white paper on buffer overflow states that part of the problem is due to the wide variety of ways buffer overflows can occur, and part is due to the error-prone techniques often used to prevent them. The paper also notes that some languages like C, C++, Fortran, and assembly, are more susceptible to overflows than others. Interpreted languages are much safer, if not altogether immune to the technique. And all operating systems are vulnerable to some extent. 5. It seems that the best defense is a well-planned and vigilant defense in depth, addressing software design and build best practices at all phases and maintaining up-to-date OS patches needed to address current vulnerabilities as they are identified. Final note, this article would not have been possible without the incredible collaboration of my colleagues, Stephen Griffin and Wes Bailey. Stay tuned, we will be attempting to conduct a modern Stack Overflow exploit without safeguards shortly. 7 references. 1 James P. Anderson. 1972 Computer Security Technology Planning Study.
Yeah, so I would have preferred to read myself, but actually, let's read these. So how did they end up in this order? Only open 2. Okay. Okay, this was a PDF. Okay. So this might be something to DTS while I'm doing something. Maybe not everybody thinks the \x doo-doo \s doo-doo is fun, right? Or, well, nice. So I was like, oh, WASP, isn't that like a web stuff? But I guess it's all connected, right? So yeah, so since I started programming when I was like a kid, a preteen. I always, you're always trying to be safe. That's the way it is, right? And when I had it in school, not like the 7th grade, my teacher was very like... That's who taught me to I always do this. Then you start writing in the middle. You do this with everything. Lots of these kind of things, I don't know. And also with input, I've always been thinking like, you don't do that. Yeah, you get a letter at a time from the stream, so you have control over stuff, right? I don't know. But of course, we mess up, right? The bigger our project is, the more we mess up people. Yeah, so should we do this one too? Yeah, let's put this one on TTS while I eat my ice cream.
Shellcode exploit with buffer overflow.
You can never get too much knowledge
5 minutes
or
read.
information,
July
right?
2nd, 2018. Continuing with the previous blog on life of function on the stack, HTTP URL here we explain how a buffer overflow on the stack can be orchestrated. It's an exploit to corrupt the memory and divert the normal flow of execution of a program. This is achieved by basically controlling the instruction pointer. Let's start with a very basic understanding of things like buffer overflows. Buffer overflow is a condition where the program writer forgets to do a bounded check on the buffer size, and this allows the attacker to put more data than what the buffer can hold. This data then spills up to adjoining memory areas. As an example of a stack layout.
Continuing with the previous blog. So this one is supposed to be before it. And it's not long. Well, let's start with this
Life
one.
of functions on stack. Shashank Jain. 4 minutes read. June 30th, 2018. This week we consider as to how function invocations happen and how stack plays a big role here. In coming weeks we also discuss how the stack can be exploited to one's advantage by orchestrating 1. Buffer overflows aka stack smashing. 2. RET2 libc. 3. ROP attacks. To understand the exploitations, a basic understanding of the stack and how it works is very important. The process when loaded in memory reserves a section for the stack in memory. The process layout in memory looks like this. The bottom part of the virtual address space represents the lowest memory segment while the top represents the highest memory segment. So one can make out from the diagram that the stack is growing towards the lower memory. This mental model is key when we look at how the compiler generates the address of the various arguments and parameters and how they are referenced within the function. The stack itself constitutes of stack frame. There is one stack frame allocated per function. Before we go into more details on function invocation and frames, it is important to understand the roles of some of the registers. 1. ESP. This register always points to the top of the stack. As the values are pushed and popped, the ESP is moved up and down. So in case of push instruction, the ESP value gets decremented as stack is growing towards a lower memory address. Similarly, for pop instruction, the ESP gets incremented by 4 bytes, assuming a 32-bit architecture. 2. EBP. This register acts as a pivot for the stack frame and can be used to reference the arguments and parameters of the function. This is useful as the ESP is more dynamic in nature and changes with instructions. With EBP as the pivot address, the parameters and arguments can be easily referenced. Though this can turned off while compiling by using the no frame pointer optimization. 3. EIP. This register holds the address to the next instruction to be executed. Function prologue and epilogue. Let's understand these concepts a bit deeper by analyzing a simple program. Int subtract, int x, int y. Int output equals xy. Return output. Void main, int argc. Int result. Result equals subtract, 10, 5. When main calls subtract in assembly, the following happens. 1. Push int 5 to the stack. 2. Push int 10 to the stack. 3 call subtract. This call automatically pushes next instruction after subtract call to the stack. The stack now looks like. After the call instruction the function prolog starts. The role of prolog is to set up the stack frame for the callee. The prolog does the following. 1 pushes the current EBP value to the stack. Remember at this point EBP register is pointing to the EBP value stored on the caller function frame. 2 moves the ESP value to the EBP. 3 setups the space in stack by moving the ESP to allocate space for local variables. Once prolog is set the arguments are operated upon and result is stored in the EX register. Post the prolog the stack looks like. Here we can see the ESP is dynamic but EBP is pivoted to the address holding the EBP of the caller frame. By this mechanism a linked list of EBP is achieved and stack trace can easily be obtained by traversing the linked list. Once the function finishes, the epilogue of the function is called. This entails the following. 1 move ESP to the EP. This effectively cleans up the callee scratch data. Though technically the values still exist on the stack, but since ESP has moved the values are not referenced. 2 pop the EP. This puts the stored EBP, remember this was the EBP of the caller, onto the EBP register. 3 RET. The RET instruction is effectively putting the current ESP value into the EIP. This has the effect of a jump instruction. Remember we had the return address stored below the EBP. Once EBP is popped, step 2 above, the ESP point to the return address on the stack. Once RET is called the value is popped off and moved to EIP. The ESP moves towards a higher memory address. Post the prolog the stack looks as below. The EBP is not shown here as now it points to the caller EBP value. The ESP is moved further down in the caller by having 2 pop instructions or by adding 8 to ESP. This depends on how compiler optimizes the machine code. This understanding of how functions are laid out on the stack and how the invocation changes the various register values is key to understanding of how a stack overflow attack can be orchestrated. We will take this up in the next blog. Updated with next blog, HTTP URL on shellcode exploit using buffer overflows. Disclaimer, the views expressed above are personal and not of the company I work for.
This chocolate ice cream is you know, it's not sweet, it's kinda strong. So, this was much better, I think, than the TryHackMe room. I'm explaining this, though the more times you hear or read it, the more it's like stuck in your brain. So I could repeat this several times, and people will probably not think this is fun, would they? Well, I'm still doing this for my sake, right? So so we have ESP. That I should. When I did assembler long ago, there was no E there. Then it's if we just like parentheses the E's, then the names are much more logical, right? So SP stack pointer points to the top of the stack. Yes, logic. So it moves up and down as we add and remove stuff. Well, not really remove, as we said, but a EBP. This retracts as a pivot for the stack frame and can be used to reference arguments and parameters of both of the functions. Useful as the ESP is more dynamic nature and changes with instructions. EBP. So it's is it like B for base? Yeah, so I was like, I'm not eating any cookies, I'm not eating any ice cream or anything. Now I felt a bit like off yesterday and today. And I'm thinking I don't want to lose my voice again. That's also a reason to TTS a lot. Yesterday I was like, you know. Yeah, I shouldn't read it loud. Can be turned off while compiling. No frame optimization. No frame pointer optimization. So I'm curious. I have to Google. And I'm thinking Google is not the best for this, maybe? Well. Oh, sorry. That character has a special meaning for OBS. It's soon. Oh gosh. I shouldn't hold ice cream in one hand. I should put it down. 1991. So this is long after I used assembler for PC. I've used it for tiny processors, you know, like Pix and Tomegas and stuff. So it was added in 91. Or what? Let's see. This is something totally different. Right? Yeah, that's why I was thinking this is not good, right? Or yeah, now we're having genes. So this is why I'm thinking. When was this as context in another way? Mm, 85? Yeah. Yeah. But that's not 85. 386 didn't come 85. What about BP? Only BP then. So, actually, since I don't think I should read it all.
The EP, extended base pointer, register was introduced as part of the Intel 80386 microprocessor, which was released in 1985. The Intel 80386 was the first 32-bit processor in the x86 family, and it introduced several new features, including new registers and instructions, which greatly enhanced the capabilities of the x86 architecture. Historical context and purpose of EP. Register introduction. The EP register, along with other extended registers, EX, EX, X, EX, ESI, EDI, ESP, was introduced with the 80386 CPU. These registers were part of the transition from 16-bit to 32-bit computing, extending the existing 16-bit registers, example BP to EP. Function in stack frame management. EP is commonly used as a frame pointer in the context of managing stack frames during function calls. It helps in accessing function parameters and local variables consistently within a function, even as the stack pointer, ESP, changes due to push/pop operations. Usage in assembly language. In assembly language, the EP register is typically used to set up a stack frame at the beginning of a function and to clean it up at the end. Here's a simple example in assembly showing how EP is used. Assembly. Push EP, save the old base pointer. MOV EP, ESP, set the new base pointer. Sub ESP, 32, allocate 32 bytes on the stack for local variables. Function body where local variables are accessed relative to EP. MOV ESP, EP, clean up the stack. Pop EP, restore the old base pointer. RET, return from the function. Summary. Introduction. The EP register was introduced with the Intel 80386 microprocessor in 1985. Purpose. It is used primarily for stack frame management during function calls, providing a stable reference point for accessing function parameters and local variables. Usage, commonly seen in prolog and epilogue code in functions to save and restore the base pointer, and manage stack frames. The introduction of EP and other extended registers marked a significant advancement in the x86 architecture, enabling more complex and efficient programs by leveraging the enhanced 32-bit capabilities.
So I'm thinking, even if it was from, I didn't have it in 1985, I think. So I guess I started about then, was 10. Or I became 10. But I had an IBM XT, which is an 888 for a bit. But it also was cool because it had the green screen, and everything later. Yeah, early 90s. So it was not like everybody had like schools and stuff, So I'm sure we had like maximum 286. So first in the early 90s it was common in personal computers. So yeah, it was like 85. No, I don't think so. And what is it that's so noisy? Can't see a thing. Lots of buzz. Sounds like some big truck is like pulling something. Should I close the window? Well, let's just continue. So, tell me if it's horrible, the noise. I guess it will stop soon. I didn't realize until now. I don't know how long it's been going on. Yeah, so that's us like digging into how and how it's B for base, as I guessed. Save the old base pointer, set a new base pointer from the stack pointer. And yeah, should I close my window? What do you think? Just tell me, I'll do it. It's 29 degrees inside and outside, so it doesn't change much in temperature. I'll close it. So I'm a bit curious too. Let's see. So it's too far up or down the street, so I can't see it actually. Maybe if I put my head out the window. So the only thing I saw through like greenery was right, my towel was someone in yellow clothes. That's all I saw. So I can still hear it. I think it's not as audible for you. We'll see. Yeah, so I want to know all the things, you know, so that I can understand the base, so I can build on that and learn all the things on top. If you start like on the top and you try and understand everything, you won't. You know, you need to have all the basics. Maybe the year is not interesting for someone else who didn't do this like very long ago. So I'm curious, like, did I ever use this? I don't think so. I don't think it existed. You know, tinier presses are so much more simple than these. So let's check this thing out that it did here. And I meant to start reading. Should I? I select stuff to read. So we understand the program. It is extremely simple. And if you don't understand it, ask. So it's assuming stuff here, right? It's assuming that there will be 16 bytes. And it does this by, well, deducting that there's a saved base pointer here. Let's look at the code again. So in the main function, we don't have any variables here. Well, I guess you could see that the arguments are in here. I need to know, right, so what I need to do is to first compile compile a basic hello world like thing, right? And then look at this in assembler. Disassemble it, see what it looks like. And then we do it with a bit more complex stuff, one thing at a time. That's what I need to do. So we can see exactly what instructions it calls and how it is compiled, simply. Kids running in the stairs. Yeah, so I need to do that. I don't... Why not do it on stream? Right? What do you think? Why not? So instead of doing this on this box, we really should do this on our own machine. Because this is just to learn just exact buffer overflow. But to really understand this, we should do it here in the Kali ones. Let's think. Do I have all the things from here that I want? Here we can see there were much more functions when it's actually running. and they also have totally different addresses. Extremely different. And these are so low. And if anyone in stream know why I always get this value, this is a big problem for me. Why I always get this every time I run this. So, first of all, is the box still up? So here's the one that's actually here. So yeah, so it is still awake. I'm just trying to find the TryHackMe page there. So 3 minutes. That's why I was thinking it has to run out soon, right? I hate what am I getting, a cold or something? I didn't bike to work yesterday or today. I was going to do it all week, I thought. Well, anyway, so we don't really need so let's open a new tab, and I think actually G++ is what I'm using for my one. But let's make something basic. So let's I don't have any directory for this. I had an ASM one, but I think yeah, it's still there. This is not the place to do. This is the tiny text test in August 2023. So oh, okay. Why? First of all, why does it have these permissions? Yeah, I did get it recently. Yeah, so I'm thinking I don't want programming, do I? Prog, maybe. Whatever. I'm never gonna type the whole name again anyway, right? So let's move us to programming. Let's see the programming. And let's look in here. Let's make their CDC. So it's nano. Let's do a hello.c, right? And we have a basic code just close by, don't we? So I don't have to copy stuff. Well, actually, why not, right? Let's make the compiler tell us what we need to include for a basic. So so main is an int, and I don't remember these in my head, do I? We don't really need them, do we? Let's test the compiler, right? So oh gosh, I don't want 8 spaces. I want 4. What am I doing? Why do I change? How do I change those in Nano? I don't care, do I? I'll just space them instead. This was a tab. We don't have a good editor. We're using Nano. Okay, I'll have to accept that. So let's just do printf, and I'm assuming we'll get errors, right? And let's do a hello error. We don't have to do hello world, do we? A short one, and I'm assuming it will tell us you need to do this and that, right? So let's GCC not static, just hello. hello.c. Oh, hello. And it will tell us implicit declaration of function printf. It's a warning though. Did it actually do it anyway? Yeah. So we don't have to add include stdio if we don't want to. Right? This is a bit funny. If we do hello now. Oh, sorry. Let's actually. Yeah. Hello. So, should we include stdio just for niceties, right? We could do it. But I don't want to add more than we need. So, include. Oh, what happened? Stdio dot. No, not dot. Just right. Let's see. It's H, right? So this is the changing. And what if we GCC it again? We shouldn't get the warning, right? So we can now see that the file is, well, I can do it again. Let's see if the minute changed, right? Now we have 16:08. So I was thinking, how slow was I, or how quick was I? I don't know. But now it's the same minute as we were currently on when I started doing it. So what we want to do now, we want to look at this one. So I'm thinking we have GUI, right? So why not make it GUI, time for GUI stuff. So there can't be a simpler file, can there? So you can change the look and feel of tools by edit options. Oh, we never would have guessed. And we don't want to go to Valley, we want to go to new project, I guess. Non-shared. This is annoying. Do we have to create projects for stuff? This is hello anyway. And import file. And this is when I needed to use it. But I did actually not really use Kira for it. I used the R2 instead. another command line thing too. Oh, the graphical stuff. We know like graphical stuff, do I? Executable and linking form DLF. Language. Destination folder. Right, so where will this end up? Whatever. Why not explore it when we can, right? So this is a tiny thing. It is, well, it's not mega tiny because it's 15,000 characters long. So I'm taking the opportunity to read all those things there. So, why that? Yes, well, let's do it. What does this mean? It will try and make C code of it. I want to look at this listing here. Whatever, let's let it analyze it.